Hi everyone, Dr. Boon here. Welcome to EdXP. EdXP is a smart educational platform that allows students to learn as well as assess themselves online. In this video, I will be sharing a topic that is common to all students taking the IB Math syllabus. And the topic is sequence and series. Whether you're doing AI, AA, SL or HL, this topic is definitely coming up for the examinations, and it is usually taught at the beginning of the year. So let's jump right in. Before we begin, we need to understand what is the difference between a sequence and a series. What are some examples of sequences? Let me list a few. For example, we have a simple sequence like this, 2, 4, 6, 8, ... Okay, this is a sequence of even numbers. Right? You can also have a sequence that is maybe, some of you may know, could be a good IA topic. Anyone knows this is the Fibonacci sequence? It's a very popular mathematician. You can also have sequences like this. Okay, you may have guessed it. This is actually the sequence of numbers in pi. Okay. You can also have a very weird sequence like this. A sequence is simply an arrangement of numbers in a particular order. You can have things like this. Take note that a sequence does not need to have a pattern. It is simply a sequence or an arrangement of numbers in a particular order. Okay, for a series, it's much more straightforward. Series will be the sum of the sequence. Okay, so instead of putting a comma here, all these commas, you can change it to a plus. Okay, I think you guys understand what I mean. In this video, I will focus mainly on the two subtopics, which focuses on two particular sequences, special sequences. The first one is the arithmetic sequence, and the second one, the geometric sequence. For these two sequences, you will need to know, number one, the general term. Number two, how to prove that a sequence is arithmetic or geometric. And number three, the sum of the sequence. I will be talking about these in this part of the video. The first thing we need to know about the arithmetic sequence is the general formula, and what really makes an arithmetic sequence. Let's say I have an arithmetic sequence over here, and I tell you this is an arithmetic sequence. Some of you might be familiar, you might have learned this before in your younger days in school, because you might have seen this pattern, but we are in the IB syllabus, we officially learn the general formulas for this pattern. The first thing we need to know is actually, the first thing we notice is actually there's a first term over here. In the IB syllabus, it is usually given the symbol A. And we also have +3, +3, +3, and so on. Does anyone know what the green arrow represents? It has a proper name. It is known as the common difference given the symbol D. So we have the first term and the common difference. We can actually start listing out some of these numbers later on in the pattern. We obviously know that the first term, which is U1, by the way, some schools use U1, some say T1. Okay? These are some of the common terminologies. The first term is obviously 2. Second term, if you notice, actually 2 plus 1 common difference. Oops, second. The third term is 2 plus 2 common differences. And the fourth term, let's do a bit more, 2 plus 3 common differences. We start to notice a pattern. And we can actually conclude that the 10th term is actually 2 plus 9 common differences. Okay. We can even go on to say that the U100th term, we can find any term we want. The 100th term in the sequence will be 2 plus 99 times of the common difference. Okay, let me extend this to the general formula. Okay, if I rewrite out generally, the first term is A, the second term is A plus D, the third term is A plus 2D, all the way to infinity, for example. Okay, in this case, we can see that U1 is A, U2 is A plus D, U3 is A plus 2D, and we can actually find the general formula UN, which is, anybody wants to give it a try, feel free to pause the video, A plus N minus 1D. And there, we have our first formula that we need to know for this topic, the general term for an arithmetic sequence. And the next thing we need to know is how do we prove that the entire sequence, let me use orange, how do I prove that this entire sequence is arithmetic? One of the mistakes that students make is what we call insufficient proof. Okay, another section over here. Insufficient proof occurs when you simply prove that, for example, U3 minus U2 equals to the common difference, or U10 minus U9 is equal to the common difference. We can't do this. We have to prove for the entire sequence. How do we do this? We can generally express UN minus UN minus 1. So the term, subtract the term before it, must give me a constant, which happens to be the common difference. Another formula that you can use is to take a UN plus 1, subtract UN, and you get a constant. It doesn't matter, as long as you take a term and you subtract the term before it. If it gives you a constant, it must be an arithmetic sequence. Next, we move on to the sum of an arithmetic sequence. Let's use an example. For example, I want to sum 100 terms, starting from 1, let's keep it simple, 1 plus 2 plus 3, all the way until 100. So the last 3 terms will be 98, 99, and 100. How do I do this without a calculator? Some of you may have done this before, but I would like to demonstrate how we arrive at the general formula. So what I'm going to do, I'm going to repeat this, but I'm going to swap the order of this sequence. And what happens if I add both equations together? I will get, on the left-hand side, I get 2 as 100. So 2 times the sum of 100 terms. And if you notice over here, let me use green, we can see that we can kind of bag our numbers here. Okay, we can even bag these numbers. And they correspond to a value of 101. And there are a total of 100 green bags. I'm sure you all agree, which means that the sum of 100 terms is 10,100 divided by 2, which happens to be 50, 50. Simple, okay? But what we want to do now is to extend this to the general term. Let's try. So let's say I want to sum n terms. Okay, so the first term we know is A. The second term is A plus D. The third term is A plus 2D. Let's use the same number of terms, yeah? So a lot of students struggle at this part here. But don't worry, the last term is actually our general term because it's the last term is the unth term, which is a plus n minus 1d. A plus n minus 2d is the second last term. Okay, it's always one common difference less. A plus n minus 3d. Okay, so we're summing to n terms. Same concept, I'm going to rewrite it, but I'm going to flip it. Okay. So a plus n minus 2d, a plus n minus 3d. Just reverse the sequence here. So a plus 2d plus a plus d plus a. Okay, just reverse my first row here. And again, let me do that. Sum of both equations. On the left-hand side, I have 2 twice Sn, 2 times Sn. And again, let me draw the same bag as what I did up there. You can see that each bag is worth 2a plus n minus 1d. And we have a total of how many bags? How many green bags? If I were to circle, if I were to group all of them, okay, you will notice that we have n bags. Yeah? Therefore, this brings us to our general formula. The sum of n terms is actually n over 2, 2a plus n minus 1d. Let me highlight this. So this is the second formula you need to know. Third formula, actually. So you will also need to know the proving formula. 3 formulas for the arithmetic sequence. I will move on to the next sequence in the syllabus, which is the geometric sequence. Let me give you an example. Same thing, we need to know the general term and proving for this unique sequence. So let me give you an example. Let's say we have this sequence over here. 721, 63, 189, 567, 1701. And I tell you that this is a geometric sequence. First thing we notice, of course, similar to the arithmetic, we have the first term here given the symbol A. Very different this time. Instead of addition, we have a multiplication of 3 in order to get the next term. Okay, this is also given a certain terminology. This is called the common ratio, given the symbol R. Okay, so we need the first term and the common ratio to try and get the general term of a geometric. Similarly, we can list out the terms. If you can see that U1, the first term is obviously 7. The second term is actually 7 times 3, or 21. The third term is 7 times 3 times 3. Okay, we can continue. Maybe let's do a bit more. The fourth term is 7 times 3 times 3 times 3, so that's 3 cubed. We can go on, we can find the 10th term, any term we can find, as long as we have the first term and the common ratio. 7 times 3 power 9 in this case. Okay. And the 100th term, if we continue on, is 7 times, anybody? 3 to the 99. Okay, so we can find any term we want. So the general term for this will be 7 times 3 to the n minus 1, if we think about it. Okay. As usual, I will extend this to the general formula. So for the general formula, you can see that the first term must be A. The second term is A times R, AR squared, AR cubed, and so on. Okay. This is quite straightforward. So U1 is A, U2 is AR, power 1, just to show. U3 is AR squared. The power always differs by 1, which means that the general term is UNAR to the n minus 1. And there we have derived together the formula for a geometric general term. To add, we also need to prove. Let me add a small section here. Again, please see my explanation above for insufficient proof. But in order to prove that a sequence is geometric, we need to prove that the entire sequence is geometric, not just a few pairs. That is insufficient proof. Okay, so to prove that a sequence is geometric, we take the general term and we divide by the previous term, and it must give me a constant, which happens to be the common ratio R. Alternatively, you can also do UN over UN minus 1. Same thing. Important thing is you have to get a constant, which is the common ratio. Next, I will move on to finding the sum of a geometric sequence. So let's use an example. Maybe I want to do the sum of, let's say, the first 8 terms of a sequence. First term maybe 2. Okay. Common ratio, maybe we do 3. So that will be 2 plus 6 plus 18. It's 54. Okay, so this will be a common ratio of 3. First term, 2. 8, 4, 3, 7, 4. Okay, so I'm just multiplying by 3 to get the next term. In order to get the general formula, what I will do is multiply by the common ratio, which is 3, to the entire equation. So what do we get? 3 S8, 3 times S8 on the left. And over here, what do we have? 6 plus 18 plus 54 plus 162. Okay. 4374. So what we're doing is just we're multiplying by 3 to the left and right. This number is slightly larger, 13122. Okay. And then what I'll do next is I will take equation 2 and subtract equation 1. Okay, what do I get? On the left-hand side, I get 2S8. And notice, this is important, that the terms kind of cancel out. 6 minus 6, 18 minus 18, so on and so forth. And I am actually left with 2 terms, right? This guy and this guy, which results in 13122 minus 2. See, from here we can solve. So the sum of 8 terms will be 13120 divided by 2. Okay. That will be 6560. I'm going to apply the same thing generally. Let's try. So let's do Sn, the sum of n terms for geometry. Okay. So the first term we know is A. Second term is AR. Zoom out. Let's do one more term. Yeah? So AR squared. And we're going to do it to the Sn term, which is actually the general term, Un. The last term is Un for Sn. And then we have ARn minus 2 here, the term before it, and the term before it, ARn minus 3. Same thing, I'm going to do what I did previously, multiply by the common ratio. So I'm going to have on the left-hand side RSN, which again AR plus AR squared plus AR cubed all the way to ARn minus 2 plus ARn minus 1. And there's going to be a ARn over here. That's the last term. Then I'm going to take equation 2 minus equation 1. Okay. Running out of space, but what we will notice is that RSN, sorry, if I were to take equation 2 minus 1 again, R minus 1SN, yeah? R apples minus 1 apple. And we start to notice on the right-hand side what happens. Again, terms start to cancel out. Everything cancels out actually. Okay. And we are left with 2 terms again, this guy and this guy. So we have ARN minus A, which brings us to, if I make Sn the subject, I get Sn is ARN minus 1 over R minus 1. And there we have derived the sum of a geometric series, which is the third equation you need to know. Not forgetting how to prove, yeah? So for each AP, arithmetic and geometric sequence, you need to have these three formulas. Okay, before I come to sum to infinity, perhaps I can sum up what we have learned so far. So the first one is the general term for an arithmetic progression is given by A plus n minus 1d. Okay. The proof, we must prove that every term, subtract the term before it, gives me a constant. Okay, you can also use the other formula. I prefer the second formula because I don't have to deal with negative signs. Yeah, either one works. And the sum for an arithmetic sequence, n over 2, 2a plus n minus 1d. Okay, let me put some headers here. And for a geometric general term, we have proven it to be ARN minus 1. The proof is that we take a general term, divide by the term before it, or we can also do the same thing. As long as you take a term and you divide by the term before it and you get a constant, it must be geometric. And of course, the last one, the sum of a geometric series given by AR n minus 1 over R minus 1. You can also do the other version, which is the same thing. Both are the same. So these 6 formulas are actually given in your formula sheet. You don't have to memorize, but after a while, you should be able to know them by heart to save time in the examinations. Okay, there's one bit left, which is the sum to infinity of a geometric sequence. Let's use an example here. Let's say I have 64 plus 32 plus 16 plus 8. I can go on forever, but we all know that the first term is 64 and the common ratio is half. Okay, so this is a geometric sequence. And if we were to actually find the sum of this series, we can actually find the sum because it kind of converges to a finite value. I like to give the illustration of maybe a grassy field. So imagine if I have a grassy field of 64 meters squared, for example, and then I add 32, I add 16. See, I'm adding my terms as we go along. 8, 4, 2, 1. If I continue this forever, it will never end. However, you will notice that it kind of converges to a finite value. So let's try to find this using what we just learned. So the sum of a geometric progression is given by what we derived earlier on. Okay, and in this case, the first term is 64. Common ratio is half. Power to, let's put this to infinity, yeah, over 1 minus half. Okay, n is going to infinity actually. And the answer we get is actually 64 divided by half, which is 128. So this is actually the sum to infinity because this term over here goes to 0, approaches 0. So we can eliminate this term. So the sum of a geometric is, for this case, the sum to infinity. So I'm going to change the symbol now. Is actually 128, which is actually the area of this grass field over here. Okay, so these are the important formulas you need to know. Let me add the sum to infinity over here. Is actually given by A over 1 minus R. Okay, I'm going to highlight this. This formula is very important. You can use it. It came from the geometric sum, but we can actually eliminate the r to the power of n term to get a over 1 minus r. What is important actually is actually that to fulfill the sum to apply this formula, a over 1 minus r, firstly, n must go to infinity. So it's a sum to infinity. Number two, if you think about it, the common ratio must be between 1 and minus 1. Otherwise, it will diverge. Okay. Only when n goes to infinity and the common ratio is less than 1 or greater than minus 1, then we can use this formula because it converges to a finite value. Okay, this is very important. Let me highlight this as well. The conditions for sum to infinity to be used. Okay. I've come to the end. Maybe I'll share some extra tips. Number one, for the arithmetic progression, AP, n over 2, 2a plus n minus 1d. We can actually rewrite this to n over 2, a plus n minus 1d. And we notice that this is actually the general term for the last term. Okay, so in some textbooks, you will see a plus l, where l is the last term. Some other common formulas that may not be present in the formula, if we think about it, un is actually sn minus 1. Why is this so? If I add many terms, okay, all the way to Sn, for example, this is Sn, and when I subtract Sn minus 1, I'm left with the Un term. I've come to the end of my short lecture on arithmetic and geometric sequence. Please feel free to log into our EdXP app and try some of the practices. What is important is that if you look at this summary over here, you don't actually have to memorize the derivations or how these equations are derived because they're all in your formula sheet. Okay, so if you really want to, you can take them wholesale and apply them in our EdXP learning platform. This is my account. You can click on either subject, for example, AA higher level. We have all the different topics here. So for example, sequence series, which I just went through, you can choose to train or assess for this concept itself. So let's say we want to start training. You can choose your difficulty level, maybe level 1 or level 2. You can choose, do you want paper 1 or paper 2? And then you can start doing some of these questions. The app will track your progress and you can gain experience points as you go along. So this is in the training mode. And also you can choose to assess even at the sub-concept level. You can even take an assessment for this sub-concept and test your understanding of this topic. So these are some of the questions. That you can try. We have come to the end of the lecture. Hope you have enjoyed it and learned something from it. See you soon in our next video. Thank you.